Hello and welcome to our traffic modeling, simulation and control project. We have topic number 5, fixed time traffic light optimization with GA, and we are going to present how we approached this problem and what results we got with my partner Nguyen Van Vin. So to first give a brief overview of this topic, we have to implement a classical four-leg intersection into Sumo and define a genetic algorithm which then connects to Sumo using TraceCI that controls these traffic lights and finds the optimal time for them. So there are 4 fixed time traffic phases. The traffic cycle is 90 seconds long, and the traffic flow is 500 vehicles per hour in each leg with a plus minus 20% standard deviation of a Gaussian distribution. And of course, since we have this genetic algorithm, we also have a fitness function where we aim to get the lowest CO2 emission as well as travel time. So among the available solutions, optimizing traffic lights is one of the most cost-effective since it improves efficiency of existing infrastructure without the high costs or space requirements of building new roads. And by determining the optimal phase distribution for a fixed 90-second cycle, this project shows how computational intelligence can meaningfully reduce waiting times and environmental impacts in realistic traffic scenarios. So, in order to understand the genetic algorithm in detail, we decided to first simplify our main scenario number 3. And so we first simplified it to scenario number 1, where we can see that traffic is only coming from north and west, and they are only able to go straight. Then in scenario 2, traffic is coming from all directions. However, they can still only go straight. And in scenario number 3, the vehicles are coming from all directions and they can also move in all directions. And with this, we're simplifying the main scenario into easier steps. We're able to really understand how this genetic algorithm works and then build it up step by step. So at this point, we defined the problem, the topic, and we know what to do, and we tackle this issue by, of course, writing the genetic algorithm, and this was done within MATLAB. So as we can see here, there's just a brief overview of what MATLAB scripts we have and what they include. I do not want to go too much into detail about the MATLAB script. That is also uploaded with the documentation and the video itself. Therefore, in order to see into the MATLAB code, I kindly ask you to refer to the uploaded MATLAB scripts. So here we have the GA traffic light final MATLAB code. This includes the population size, the generation size, the crossover, as well as the mutation. We have the run sumo MATLAB code, and this includes the set phase functions as well as the fitness function, normalization, and it includes the part where we change the traffic flow. So regarding the fitness function, as I mentioned, we aim to minimize the travel time as well as CO2 emission, and we can see how it is defined here. Of course, we could use additional variables to this, but this project only focuses on these 2, and then we could adjust the weights of these variables accordingly. And of course, we have to use normalization in this case, since the difference between travel time and CO2 emission is very big. So the run sumo includes the change traffic flow MATLAB code. This includes read line methods and write line methods, and that includes the Gaussian traffic flow MATLAB script, which, as already mentioned, includes the part where we change the traffic flow according to a Gaussian distribution. And we also have the normalization function within the run sumo MATLAB script, which, as I already mentioned, normalizes the CO2 emission and the travel time. So even though I mentioned I do not want to go too much into detail, I think it's still important to provide some snippets of the code where important information is displayed. So here we can see that we define the population size for 5, max generations for 5, crossover fraction for 0.8, and then in the bottom we can just see how we defined the Gaussian traffic flow as well as the normalization function. I would like to show a short clip of how this genetic algorithm actually works. And for this, we have a video where I'm going to show a part of it. So as you can see, we run the GA traffic light final MATLAB script, and this will automatically open the Sumo environment that we modeled with the respective traffic flow, and this will just go on and on for a few minutes, and then we'll eventually get the results. So regarding the results, I'm going to present the results for scenario number 3. On the left side, we have this table, and in the left column, we have the number of generations, which are 5, 10, 15, and 20. And in the right column, we have the optimal populations, which is the duration of the state in seconds. The graph highlights the cyclic nature of traffic congestion on the 4 intersection legs, exhibiting a distinct square wave pattern, and the elevated plateau corresponds to the red signal phases, where pretty much vehicles accumulate, and this results in a temporary spike in queue length and waiting time. Crucially, the graph shows that these queues successfully dissipate during the green phases, as indicated by the regular throughs. And this behavior demonstrates that the GA, the genetic algorithm, has identified a phase duration sufficient to clear the accumulated demand within each cycle, preventing the onset of cycle failure or a even permanent gridlock despite the heavy traffic load. So here we again have the same table, there is no change here, but the graph is now regarding the CO2 emission. And a comparative analysis of the travel time, so the previous one, and the CO2 emission, which is this profile, reveals the intrinsic physical coupling between intersection delay and environmental impact. While the travel time graphs exhibit clear plateau, representing static queues during red phases, the corresponding CO2 graphs show a more volatile behavior. Notably, the most severe pollution spikes do not occur during the peak delay, so during idling, for example, but rather during the transition phases when the signal turns green. This indicates that the acceleration inertia of the discharging queue generates significantly higher instantaneous emissions than the static wait, highlighting a critical trade-off. Minimizing travel time by flushing queues quickly may inadvertently trigger sharp transient spikes in fuel consumptions and CO2 output. So future improvements, of course, this could be applied to bigger intersections as well as different types, but this would conclude this presentation, and I would like to say thank you for your kind attention and the support throughout this semester. That is greatly appreciated. Thank you.